Hello. In this video I am going to explain how to solve a non-linear equation using the Newton Raphson iterative method. This method is based on the Taylor series. According to the Taylor series, a function can be written as the sum shown. If we ignore all numbers after the two first expression as they have a smaller value, we can write the function as shown. Next we set the function equal to 0 and we get the equation of the Newton Raphson method. As said, this method belongs to the iterative methods. Each time we calculate a more precise approximation for the answer. When the value of the relative error of the approximation is low or equal to 0, the method can stop. The relative error is calculated as shown. When the relative error is very close to 0, we have a very good approximation of the solution, and when it's equal to 0, we have calculated the exact solution. Let's see an example to better understand the method. We are asked to solve this non-linear equation, where x is between 0 and 0.11, using the Newton Raphson method. The Newton Raphson method belongs to the iterative methods, therefore to begin we need a first approximation. For most exercises you will find the first approximation will be given. If not, a good way to calculate it is the one I'm going to show you. If we look at the graph closely, we can expect the solution to be a little above 0.06. For this reason, a good first approximation close to the answer will be the average of the limits of our interval. So to calculate our first approximation, we find the average of the limits of our interval as shown. It is important to have a good first approximation so that the method converges after only a few iterations. Now that we have a first approximation, we can begin the iterations to begin approximating the solution. Let's begin the first iteration as shown. Firstly, we must calculate the derivative of our equation. Now that we have calculated the derivative, we can perform the first iteration to calculate the second approximation. We can see that after one iteration the relative error's value is already small. Let's perform the second iteration, with the exact same steps. We can see that after only two iterations the relative error's value has decreased significantly. Let's perform another iteration, with the exact same steps. We can see that after our third iteration the relative error is equal to 0. We have calculated the exact solution. The fast converge of the method confirms that not only the method is effective but that we have chosen a good first approximation.